So let's try and do some applications of Coulomb's law, because this is really what it's going to boil down to when it comes to doing homework and stuff. So let's calculate the net force on particle Q1 due to the other two charges. Right? If it's just two charges, it's easy. We just say Coulomb's law. I tell you the distance, and the answer's there. Right? But now I've got this charge. I want to know what the force on this guy is, but there's two other charges to deal with. Right, so as we walk through this, I'm going to do a quick review for you guys of stuff that most of you probably already know. You needed it to do a lot of stuff in 1A, but I know because we're off sequence, not everybody took it so recently. So let's just go ahead and take a few minutes to review. But first of all, let's talk about kind of the general scheme of how to solve these kind of force law problems. First thing to do is to define a coordinate system, right? Because we're going to be talking in terms of x or y, so we have to know what we're talking about. Most logical thing is to make x point in that positive x direction, in the forward right direction to the right. Then we're going to draw an accurate diagram of the problem, but it's already there, right? But sometimes you'll get a word problem that doesn't tell you, so we're good. We just add the x direction. And we're going to list all the known quantities. This is a particularly useful thing to do if you don't take the time to do it. It's a little bit, maybe a little bit faster in the short run, but if you ever end up having to go back and redo a problem or something, you'll find that in the long term, it's a better strategy. Yes, they're all here, but I find it very nice to kind of just jot down all the quantities in a nice, easy way to look at them. All right, so what's our next step? If I'm going too fast, I'm kind of assuming that you guys can follow along because the notes are available, right? I'm not expecting you guys to be jotting stuff down at this speed, right? But if anybody feels I'm going too fast, you let me know. If you're embarrassed to say I'm going too fast now, email me afterwards, and then I'll put it to a vote. I'll put a clicker question up. Am I going too fast, right? Because I don't want to talk and have nobody understand. Then that's wasting everybody's time. Okay, so now what we're going to do is we're going to calculate the magnitude of each force separately using Coulomb's law. Okay, so this starts to get at the idea of superposition. That we can break things down and look at things pairwise, and then we'll add them up at the end. Right, so let's start by writing out Coulomb's law, because we know that we're going to be using that. And we're going to look at the force on 1 due to just 2. We're going to pretend this guy isn't here, right? And that's just, we write out Coulomb's constant. Q1 is this guy. Q2 is this guy. It doesn't matter, they're actually labeled differently. Right? This is generic 1 and 2. We're going to use it for 1 and 3 as well. Right, so the two different charges are there. The separation between them is 0.3 meters, but we have to square that. All right? And we do the same thing for the force due to 1 if 3 was the only one that existed and 2 did not. So the separation, so we have Q1 being this guy, the first one that's doing the action So that's 4 times 10 to the minus 6. And here we have 3 times 10 to the minus 6, right, over here, 3 microcoulombs. And you notice that right now I have ignored the sign, right, because I'm taking the absolute values. Right? This is not going to give me a direction. It's going to just give me a magnitude. And now the distance between here and here, we ignore this one being there. That's just 0.5 meters apart. So we square that. Okay, and we plug in to our handy calculator, and we get the two forces, 1.5 newtons and 0.43 newtons. Okay, so now what we're going to do is we're going to determine the direction of each one separately as well. Right, so Q1 and Q2 have opposite charges. So F21 is going to be attractive because opposites attract. So that means that F21, since it's an attractive force, is going to pull Q1 in the positive x direction towards Q3. Right, I'm sorry, Q2. On the other hand, Q1 and Q3 are the same charge, so they're going to be repulsive, which means if I ask which way is this going to go, if it's being repelled by this guy, it's going to go that way. Right, so negative x direction for F31, positive for F21, and then we just add the forces together using vector addition, taking into account the signs. So plus 0.15 and minus 0.43, or 1.5 and minus 0.43, and we get our final net force, which is 1.07 newtons in the positive x direction. Yes, sir?
Sorry, it's a little vague, but wouldn't ignoring the sign and calculating F21 give you a different, why did you ignore it?
What I did was I ignored it, I took it stepwise, right? Because to get this law, as written just this way, is only giving you the magnitude of the force between two particles, right? They're saying nothing else exists, we have two particles, and the answer will tell you, oh, the force is 1.5 newtons, but it doesn't tell you whether it's attractive or repulsive, right? And that you can put in by hand, right? And then you do the same thing for this one, and then you come in, and if you're dealing with just one set of pairs, right, then you're done. You say, this is the force, I just use the magnitude, right, and I figure out the sign from opposites attract, right? But when you have to do more and more of them, and you start adding them up, then you have to start keeping track of the sign, you have to keep track of the direction, and it's almost like I paid you to plug this, because the next thing we will do is the vector form of Coulomb's law that does take into account the direction, which if you're only working in a line, that's easy, that's just the sign, right? But we're going to get more complicated in a moment, okay? So I'm just kind of building it up, but you're right. You normally, once you start doing problems with multiple things, you are not going to want to just ignore the sign because you'll get in trouble. Okay, like I said, perfect segue, right? Yes? When do you calculate from 2 to 3?
Yeah.
So that's a good question. So remember, whenever you do a problem-solving thing, right, the first thing you ask is, what's my goal? What are they asking me for? Right? And in this question, they only asked you for the force on charge 1 due to the other two, right? So that's what I solved for. I solved for the force on 1 due to both of the other ones. What they didn't ask you, but they could have, is what's the force on 2 due to 3, or 3 due to 2, or even 3 due to 1, right? So you can end up doing a lot of work and filling up a whole page, doing calculations you don't care about if you don't use this goal-oriented method, right? And it really is the way you want to approach life in general, if you don't mind me soapboxing a bit, right? So yes, what we've kind of done here is we're saying instantaneously when they're in these positions, if I ask you to calculate really, really, really quick, that will give you the right answer for the force on 1 due to these other guys. But unless these guys are actually glued down, there will be a force on this one due to this, and this one due to this, and they will all move, right? And now we're doing, instead of electrostatics, we're doing electrodynamics. We don't want to go there this quarter, right? Right, so we're just going to assume that the ones they don't tell you are movable are super glued down to the floor, okay? But there is a force on them. In this problem, they didn't ask us to calculate it. Good question.